Alright, so which grade is more likely to go to prom? Many high schools, prom is an annual dance that only juniors and seniors can purchase tickets for. Student council at a large high school is wondering if juniors or seniors are more likely to attend. They take a random sample of 50 juniors and find that 28 are planning to attend prom. They select a random sample of 70 seniors and find that 45 are attending. Construct and interpret a 95% confidence interval for the difference in proportion of juniors and seniors who are planning to attend prom. Alright, so remember confidence intervals. We start with our point estimate, that is our sample data. So we have two different samples, so we have to find the difference of those two samples. So let's look at this. The juniors, what did I say? They took 50 juniors and 28 of them are going to prom. Well, what does that translate to? That translates to 0.56 for my p hat 1 for juniors. Now for seniors, there were 70 seniors and 45 of them were going to prom, which translates to 0.64. Now, the way that this simulation sets it up, it's calling juniors p hat 1 and seniors p hat 2. So it says, what is the difference in proportion for juniors and seniors? So it's taking 0.56 and subtracting 0.64. And it comes up a negative number, and that's okay. 0.64 gives me negative 0.08. That just means that there are more seniors than juniors, right? Because it's subtracting juniors first. So then it says, what's the formula for calculating the standard deviation of the difference in the proportions? Well, in the previous simulation, we talked about P1 minus P2 is this guy. So P1 times the complement over N1 plus P2 times the complement, over N2. Okay. However, we don't know the true proportions. All we have when we do confidence intervals, if you remember, is the sample data. So it becomes the standard error of p hat. But all that's really changing is that we're using p hat instead of p1. Okay? So, not a big deal. I'm going to show you how to do a shortcut in the calculator with this, but we're just talking formulas for now. What condition has to be met to use this formula? Well, if you recall, to use standard error or standard deviation, we have to check the 10% condition. Okay, so let's see. Is 50 less than 10% of the juniors? Well, it does say that it's a large high school up here, so we're going to assume that is less than 50%. And then is 70 less than 10% of all the seniors? We're going to assume that's true because it's a large high school. All right, so the 10% condition has to be checked, remember, for standard deviation to work. And that's because of independence. Now, what additional conditions need to be met in order to construct a confidence interval? Well, we have to know it's normal and we have to know it's random, right? The regular two conditions we've done before. So let's check this out. Let's do this. When we do random, we have to check both samples. Were both samples random? Well, it says a random sample. Random sample of 50. 50 juniors, and it says SRS of 70 seniors. So the random condition is satisfied. All right, so we did 10% up here, we did random, and now we have to check large counts for normality, right? Because it's proportions. So is it tedious? Yes, it is, but it's not impossible. So 50 times 0.56 gives me 28. That's greater than 10. 50 times 0.44 gives me 22. That's greater than 10. And then I do the seniors. 70 times 0.64 gives me 45. Oops, that's greater than or equal to 10. And then 70 times 0.36 gives me 25, greater than or equal to 10. So it's just tedious work. It's not hard, it's just tedious. Now we get into how did we build a confidence interval in the past? Okay, remember we had a point estimate, plus or minus a z-star, right, the critical value, and then we did standard error. Okay, so specifically, what is that going to look like when we do a difference in proportions? Well, it's p hat 1 minus p hat 2, plus or minus. Z-star is going to be calculated exactly the same way, and then that whole standard error formula that we've used before, or that we have above, okay? Okay, now when I run the numbers, when I plug in my numbers, it's going to look like this. So 0.56 minus 0.64. Let's see, it's a 95, what are we building here? Yeah, 95% confidence interval. So if you remember, that was a z-star of 1.96. And I plug in my values. All right, now in your calculator, there is a shortcut that will do all of this calculation for you really quickly and nicely. So I'll show you that in a minute. But when it comes out, I finish, I get negative 0.26, comma, to a positive 0.1. All right, so then we draw our conclusion. The wording is going to sound very similar. So we are 95% confident that the interval from negative 0.26 to 0.1 captures the true difference in proportions. I'm going to abbreviate because I'm running in proportions of juniors and seniors who are planning to attend prom. All right, so yes, it's wordy, we know that. All right, now look at our interval for a second here. Goes from negative to positive, doesn't it? It says, does the interval provide convincing evidence that juniors have a lower proportion of planning to go in prom? Or is it plausible that there is no difference in the two classes? All right, so let's think about this for a second. Let's use our logic. If our interval came out with, two numbers that are negative, what would that mean? That would mean that the juniors were higher than seniors, right? For sure, we knew that, if it came out that way. If it comes out positive and positive, well, that would mean the seniors are higher than the juniors, right? However, if it comes out negative positive, that means that 0 is somewhere in that interval, right? So we can't tell. What does that mean? We can't tell if there is a difference because 0 is a possible difference between the two. So how do we say this? Well, we would say, no, the interval contains 0, so it is plausible that there is no difference. All right, hopefully that makes some sense to you. Let's summarize this and try it ourselves. Okay, on the back, what do we need to know? For the confidence interval, same 4 steps. Okay, we're going to state the true difference, and we're going to define in context, right? As always, we define. To sample, and then we plan. So here's the name of our test. It's a 2-sample T interval. That's the name of the test. New test we've added to our list, okay? We check for independent random samples, 10% condition, and large counts, all right? Independent random samples just refers to the fact that those samples were completely separate. There's no overlapping, all right? You want to look for that. In the do step, we're going to show our work, and we're going to use a calculator test. It's going to be stat test, and you're going to look for a 2 proportion Z interval, all right? And I'll show you that in a moment as we walk through this. And then, of course, we conclude in context, all right? Now, is there convincing evidence? Well, this is what we were talking about in that last question. If your interval comes out as positive, that tells you that the first proportion is always greater. If it comes out negative, whatever the second proportion is greater. But if it comes out negative and then positive, then we don't have convincing evidence. And why? That is because 0 is contained. All right? 0 is contained. Now, let's walk through this question, or maybe you want to pause the video and try it yourself. Feel free to pause it, and then I will show you those calculator steps when we get to the do step. In a social study, a random sample of 150 teachers were selected, and an independent random sample of 100 nurses were selected. Each person was asked if they currently have a second job. The results showed that 48 of the 150 teachers and 21 of the 100 teachers have a second job, or nurses have a second job. Construct and interpret a 95% confidence interval for the difference in the proportion of all teachers and nurses who have a second job. All right, so what is my parameter? I'm just going to follow the script, okay? The difference in proportion, so it'll be teachers minus nurses. So proportion of teachers minus nurses. What is that? What am I looking for? It's the true difference in proportion of teachers minus nurses who have a second job. All right, my confidence level is 95% as stated in the question. Now, before I go too far, I'm going to figure this out. Okay, so the p-hat of teachers, what did it tell me here? It says 48 out of 150 teachers, and the p-hat of nurses was 21 out of 100 nurses. So teachers comes out to what, 32%, and this one comes out to 21%. The difference, 32 minus 21 is 11, right? All right, now, name of the procedure. We could say a 2 proportion Z interval. You could say 2 sample Z interval if you'd like. Now we get into checking our conditions. All right, so random. We got to check for 2 random independent samples. All right, so what did it say in the question? It says random sample of 150 teachers. And then it says it's a random sample of 100 nurses. Okay, obviously there's no overlap there. And if you recall, why do we do this? Because we need to make sure that we can generalize to the whole population, right? We need it to be random and independent so we can generalize our results to the whole population. All right, next would be our 10% rule. So is 150 less than 10% of teachers? I think so, yes. And is 100 less than 10%, oops, sorry, 10% of all nurses? Let's hope so, right? Why do we do this? Because sometimes we sample without replacement, and that's why we have to check to make sure our sample is small enough. Okay, now we do, switch this over. Now we're going to check our large counts test for normality, right? And yes, we have to check both samples. So let's just crunch the numbers. 150 times 0.32 is 48. 150 times 0.68 is 102. That's greater than or equal to 10. Greater than or equal to 10, we're good there. Then with the nurses, 100 times 0.21 is 21. 100 times 0.79 is 79, and that's greater than 10. So we have shown it. And why do we do this? To show sampling distribution as approximately normal. All right, there's our conditions. Now, the formula. Here's what you need to know. It's a time saver. I'm not going to make you write the formula out. What I need you to do for each of these samples is this, okay? So like on this example, I would say teachers. So how many teachers? So X of the teachers was 48. N of the teachers is 150. And then the nurses. And you'll see in the calculator why we need this. The nurses, there was 21 nurses out of, N, the sample of nurses was 100. So we're going to need this information to enter a calculator. And then it's a big time saver. You don't have to show much work on this. And we know it's a 95% interval. It will calculate the standard deviation and everything for us, okay? So I'm going to switch over to the calculator real quick. All right, so if you go to stat test, go to test, go to do proportion z test. Oh no, we're doing intervals, aren't we? So do proportion z interval. So keep looking down till you see do proportion z interval right there. Now notice what it's asking me, x1, n1. This is why I had us write it out like we did. What did we say? The teachers was what? 48. 48 out of 150. The nurses was 21 out of 100. And then you enter your confidence level. So it's 0.95. And you hit calculate, and there's your interval for you. All right. So 0.000704 to 0.219. Very interesting interval. All right, so we're going to take this back to our page. Okay, so our interval is 0.001 to 0.219. So then we do our conclusion, just like we've done before. We are 95% confident that the interval from 0.001 to 0.219 captures the true difference in proportions of teachers and nurses who have a second job. Okay, so very similar to what we've done before. It's just a little more tedious when you deal with two samples, but the calculator does help a lot. All right, good luck, and we'll see how you're doing in class.